This video looks at the Lewis theory of acids and bases. By the end of this video, you should understand how the Lewis acid-base definition differs from other definitions we've looked at, and you should be able to recognize a Lewis acid or a Lewis base. While studying acids and bases, the chemist G.N. Lewis discovered that when a Bronsted-Lowry base takes an H+, it can also be said to donate an electron pair to form the bond to that H+. For example, under the Bronsted-Lowry definition, we would say that NH3 takes an H+ from OH-, making NH3 a base and H2O an acid. However, seen from the Lewis perspective, we can say that NH3 has donated the electron pair that goes to form the bond between nitrogen and hydrogen in NH4+. This electron pair here has been donated to the H+ ion. Looking at another example, according to Bronsted-Lowry, H2O takes an H+ from HCl, making it a base. However, according to Lewis, we can also say that H2O has donated an electron pair to the H+ to form the bond between hydrogen and oxygen. Therefore, Lewis acids and bases are defined in terms of electron pairs. A Lewis acid is said to be an electron pair acceptor, and a Lewis base is said to be an electron pair donor. Due to this change in perspective, all Bronsted-Lowry bases remain Lewis bases. However, the Lewis concept incorporates far more acids than the Bronsted-Lowry concept. For one, it does not require a proton transfer, making H+ just one of many acids, not the only thing responsible for making something an acid. Likewise, it's also able to address acids and bases that aren't in aqueous solution. The Bronsted-Lowry concept only dealt with acids and bases in aqueous solution. Let's look at some common Lewis acids. H+, as we've seen, is probably the most common Lewis acid. Viewed from the Lewis perspective, H+ gains an electron pair to form a bond with the Lewis base. Likewise, as we've seen, metal cations are able to form complexes, often with H2O or NH3, acting as Lewis acids. In this case, the aluminum 3+ ion attracts the electrons from water and accepts this electron pair, forming a bond between aluminum and each water molecule. This aluminum can now be called a hydrated complex. And finally, electron-deficient molecules. Electron-deficient molecules are things that are usually trigonal planar in geometry. For example, BF3. BF3 lacks a full octet on the boron. Therefore, it's highly reactive and will attract electron pairs quite strongly. Here, the electron pair from fluorine is donated to the boron atom to form the bond between that fluorine and the boron. Looking at some common Lewis bases, NH3 is quite common. This again is the same example we've seen, NH3 acting as the electron pair donor to form a bond between the nitrogen and the hydrogen. Water is another common Lewis base, particularly when it acts as a ligand in a hydrated complex. Again, we see the example with our aluminum ion acting as our Lewis acid and our water molecules acting as our Lewis bases. Water molecules that form a complex like this are often called ligands. And finally, anions such as hydroxide and fluoride. Here again we see fluoride donating an electron pair to BF3 to form a bond between boron and fluoride. That brings us to the end of this video. Let's review our goals. First, we looked at how the Lewis acid-base definition differs from others we have seen, in that it refers to electron pairs rather than protons or H+. And then we learned to recognize Lewis acids or Lewis bases.